So like I said in the last video, the dot product is extremely important. You're going to use it over and over again in different contexts. And so I want to show you a nice worked out video to show you all the steps that I'm looking for when you're doing problems and applying your conceptual information to actual physics scenarios, that type of thing. I want to show you all the steps I'm looking for. It's going to be really drawn out. You're going to see every single piece of the way. And this is what I want to see from you. You are beginners. And so I need to see every little thing. You need to be doing this for yourself, and eventually you'll learn it and it'll become more familiar. But you got to do it this way when you're first learning. So a couple of properties that were in the conceptual reference material on Top Hat that I didn't have in the last video are a few things here that we're going to use in these worked out problems. So the first property of the dot product that I want to talk about is the fact that it is commutative, that A dot B is the same thing as B dot A. So it doesn't matter the order of the vectors in the operation, you can interchange them, you'll get the same result. The next property is that it is distributive with scalar multiplication. So the dot product takes two vectors and it dots them. So if there are any scalars in the way, you can bring them out to the front. They are not part of the dot product, bring them out to the front and you can just do the dot product with the vectors. And then multiply them by the scalars afterwards. The other property is that it's distributive with addition or subtraction. That if you have A dot B plus C, you can actually distribute the dot product to both of those vectors in the addition, like within those parentheses, you can distribute the dot product. So that's the same as doing A dot B plus A dot C. So these are all properties that we're going to use in the next problems. Some common uses that I'm going to show you of the dot product. The first one is finding a projection or finding a component of a vector in a particular direction. So when you dot a vector with a unit vector, you can gain a lot of information about the vector in the direction of the unit vector. Remember that a unit vector has a norm equal to the number 1. So when you do their dot product, you'll have the norm of the vector times the number 1, because it's the norm of the unit vector, times the cosine of the angle between them. So all the information you're extracting has to do with the magnitude of your vector and the orientation of that vector with the unit vector. So this is something we'll use eventually when we start talking more about components. The next most common use of the dot product is using it to calculate norms. The definition of the norm is the square root of the vector dotted with itself. So to calculate a norm, you must do a dot product first, and then you just take the square root. And then the last common use of the dot product is using it to find the angle between two vectors. You can calculate the dot product, and you can find the norms of the vectors, and you can use the definition of the dot product to then calculate the angle between the vectors. So I'm going to show you examples of this example for finding the norm and for calculating an angle. In your homework, in your Apply Your Knowledge homework, you're going to do this one, but I kind of step you through it, so I'm not going to do this one for you in this video. But these other two are common uses that I really want you to know how to show all of your work to do these operations. So let's start out with finding the norm of a vector. This vector h is written in terms of other vectors, a and b. So vector h is some scalar m times vector a plus some scalar p times vector b. Everything is very general. I'm not giving you any numbers at all. This is all purely conceptual. We're going to work out expressions to find an equation that talks about the norm of this particular vector. So remember, the norm of a vector is the square root of the vector dotted with itself. So we are going to figure out the dot product of h with itself, and then we'll take a square root to find the norm. So let's just start off there. I'm going to distribute the dot product. I'm going to take all the stuff in the parentheses and I'm going to dot it with all the other stuff in the next set of parentheses. So I'm distributing the dot product. You might remember this as FOIL. You remember your like 5th grade math. I'm going to multiply the first terms, then the outer terms, then the inner terms, and then the last terms. I'm going to distribute those dot products. So h dot h would be equal to, I'm going to do the first terms right now. M times m, take the scalars out to the front, so I just get m squared. And now I have the dot product between a dotted with a. Now the next ones, now I'm going to do the outer terms. So m times p, and then I have vector a dotted with a vector b. Now I'll do the inner terms. So now I have, again, P times M, and then also B dotted with A. You can write B dot A or you can write A dot B. Remember that the dot product is commutative. And now the last terms. So I have P times P, that's P squared, and now I have B dot B. All right, so that was distributing the dot product or foiling out the dot product if you want to think of it like that. Now I'm just going to put in the definition of the dot product. Remember that the definition of the dot product says norm of the first vector times norm of the second vector times cosine of the angle between those vectors. So let's identify the angles between these vectors. I see a dot product that has A dot A. The angle between vector A and vector A is 0. A vector is always parallel to itself. So the angle between B and B is again 0. B is parallel to itself. The angle between A and B, you can see from this diagram up here, I've labeled it as the angle phi. So I'm just going to use that symbol phi to describe the angle between vectors A and B. So let's simplify a little bit more. I have m squared times the norm of vector A times the norm of vector A times the cosine of 0 because vector A dotted with the angle between A and A is 0. I'm going to combine these two middle terms together. I see m times p, then a dot b, and then I see it again. So really I have 2 times m times p. A dot b would be the norm of A times the norm of b times the cosine of the angle between them, which was, I call it phi. So those are my two middle terms. And now my last term, I have p squared norm of vector b times norm of vector b times the cosine of 0. Plug in, show me all this, that you know what the cosine of each of these angles is, that you know what those angles are, that they're different for each term. Let's keep on going. I'm just going to simplify a little bit more. I have m squared, norm of vector A times the norm of vector A, I can just write as the norm of A squared. Now my middle term was 2mp norm of A times norm of B times cosine of phi. Can't really simplify that anymore, that is what it is. And now this last one, I have p squared, norm of b times norm of b is b squared. And then again, cosine of 0 is just the number 1. So if you want to write times 1, you can go ahead and do that. I plug in and I know that the cosine of 0 is the number 1. That's where those went. So maybe write something like this to show me that you know that the cosine of 0 is 1. All right, so now our last thing is to actually calculating the norm of vector h is going to be the square root of this dot product that we just calculated. So I'm going to plug all of this stuff into the square root there, and I'll have my final answer. So there is my final answer for an expression for vector h, the norm of vector h, in terms of these other vectors and the angle between them. All right, so this is very similar to an apply your knowledge homework problem that you're assigned. And so you can use this and follow the steps and try to do that problem after watching this and try to see if you can do it on your own. And I want to see written out all of these steps. If you skip steps and you don't show me that you know what you're doing, I can't be sure that you know what you're doing, and I'm going to take off points. All right, our next example, this is actually the problem that was at the very beginning of the of the conceptual reference material. So this is a tough problem. It says, can you do this in under 4 minutes? And I'll be honest, this is a long problem. It's probably going to take me a little bit more than 4 minutes, especially because I'm going to go real slow and show you exactly how to do it. So if it takes more than 4 minutes, it's okay, but I'm going to try to definitely do it in less than 10 for sure to really know that I know what I'm doing. So I have two vectors, v and a. And they are written in terms of unit vectors, s hat and p hat. So I can't really picture these things. I don't know how s hat and p hat are pointing. I can't picture v and a, but I just have them written in terms of these unit vectors. And I also know that the angle between vectors s hat and p hat is 45 degrees. And we want to figure out the angle between the velocity and the acceleration vector. So v and a, that's the angle I'm looking for. So let's use the definition of the dot product. The dot product between v and a would be the norm of v times the norm of a times the cosine of the angle between them. So this is that angle that we're looking for, the angle between the velocity vector and the acceleration vector. That's our goal, is to figure out theta. So in order to do that, we're going to need to do the dot product to get the left-hand side of the equation. Then we're going to need to find the norms of v and a. And then if we know all of that stuff, then we can solve for theta. So that's the steps that I'm going to show you. First, I'm going to distribute the dot product between v and a. Then I am going to find the norms of a and v. And then I'm going to solve for theta. So that's the steps that you want to take. It's going to take a little while to work all this stuff out, but that's how you do it. So let's start off with finding the dot product between v and a, vectors v and a. So I wrote down my vectors in their parentheses, and now I'm going to distribute this dot product. I'm going to FOIL out my terms and get the dot product between v and a. I'm going to try to have as many decimal points, not round until the very end, so try to be careful about that. It could end up affecting our answer. Another thing, I'm not going to write in these units because it's just going to get really messy and there's a lot of stuff there. Let's think about the units right now. The units of the dot product between v and a would just be the units of velocity times the units of acceleration. So that would be meters per second that I see in my velocity vector times units of meters per second squared. So the units of my dot product are going to be meters squared over seconds cubed. So those are the units of the dot product. So whatever I get in the end, I'm going to get a number, and it's going to have those units. So I'm not going to put all of those things in there along the way. So let's do this dot product. So v dot a, I'm going to do the first term. So 3 times negative 2.6 s hat dot s hat. So I get negative 7.8 s hat dot s hat. Now let's do the outer terms. So 3 times negative 2 is negative 6. This time I get s hat dot p hat. Now let's do the inner terms. 1.8 times negative 2.6. I get negative 4.68. And again, it's p hat dot s hat. Doesn't matter about the order, so I'm just going to write s hat dot p hat. And now let's do the last terms. 1.8 times negative 2. And I get negative 3.6 p hat dot p hat. All right, let's plug in our definition of the dot product. It'll be negative 7.8, norm of the first vector, so norm of unit vector s hat times norm of unit vector s hat times the cosine of the angle between those two vectors. The vector with itself, so that must be the angle of 0. I'm going to combine these two middle terms. Again, I see s hat dot p hat. I can combine those two like terms, and so it's going to be negative 6 plus negative 4.68. So I get negative 10.68. And now it's the dot product of s hat dot p hat, so it's the norm of s hat times the norm of p hat times the cosine of the angle between them, which they told us in the problem statement was 45 degrees. And then the last term, I have negative 3.6. It'll be the norm of p hat times the norm of p hat times the cosine of the angle between p hat and p hat. It's a vector with itself, so it must be parallel to itself. That's why my angle is 0 in that term. So now let's simplify. A unit vector's norm is 1. So the norm of s hat times the norm of s hat is just the number 1 times the number 1 times cosine of 0 is also the number 1. So really I have negative 7.8 times 1 times 1 times 1. So that term is just going to be negative 7.8. My next term, I have negative 10.68. Again, the norm of a unit vector is the number 1. Norm of the next unit vector is the number 1. And I have cosine of 45. So if I multiply negative 10.68 times the cosine of 45, I get negative 7.552. And now my last term is negative 3.6 times the norm of unit vector p, which is the number 1, times the norm of a unit vector, so that's the number 1, times the cosine of 0, which is also the number 1. So my last term, I just get negative 3.6. So now if I combine all of this stuff together, I have the dot product between v and a is negative 7.8 plus negative 7.552 plus negative 3.6. So I get negative 18.952. And like I said, the units would be meters squared over seconds cubed, because that's just the units of velocity times acceleration. All right, so that's step number one. Now let's find some norms. Let's find the norm of vector v. So I'm going to distribute this dot product. I already wrote it out for myself. I have the square root of v dotted with itself. So norm of vector v is going to be the square root. Don't forget your square roots. It's a common mistake. I make it myself. Just be real careful. Let's distribute this dot product. So I'm going to do the first terms, which would be 3 times 3. So I get 9 s hat dot s hat. Now let's do the outer terms. So 3 times 1.8 is 5.4. And that is s hat dot p hat. Let's do the inner terms. 1.8 times 3 is again 5.4. P hat dot s hat, that's the same thing as s hat dot p hat. And now the outer terms, 1.8 times 1.8 is 3.24. And that is p hat dot p hat. Okay, let's bring it down and simplify a little bit more. Let's use the definition of the dot product. So I have 9 times norm of unit vector s hat times norm of unit vector s hat times the cosine of the angle between those two, the vector with itself, so the cosine of 0. Angle in that case is 0. I'm going to combine these two middle terms here, 5.4 plus 5.4, because they are like terms, is 10.8. S hat dot p hat, so that's the norm of s hat times the norm of p hat times the cosine of the angle between them, which is, again, for this problem, the angle between s hat and p hat was 45 degrees. And now my last term, 3.24 p hat dot p hat, so that's norm of p hat times norm of p hat times the cosine of the angle between those two things, the vector with itself, so the angle is 0. Keep on going. So that's 9 times 1 times 1 times 1 plus 10 times 1 times 1 times the cosine of 45. And then the last term is 3.24 times 1 times 1 times the cosine of 0 is also 1. All right, remember that a unit vector's norm is always 1. So it doesn't matter what the unit vector is, always has a norm of 1. All right, so my last step here is actually just plugging in numbers and taking that square root. And so I get the square root of 9 plus 10 times the cosine of 45. Actually, 10.8, sorry, I lost my 0.8. 10.8 times the cosine of 45 plus 3.24. And so I get a final answer. The norm of vector v is 4.458. And it would have units of meters per second. It's the same units that you see there in the velocity vector itself. It would be meters per second times meters per second, and then square rooted, you get meters per second back out in the end. All right, so that's my norm of vector v. Show me all these steps. I took the time to show you. I want you to show me. We're going to do a similar thing for the norm of vector a. The norm of vector a would be just the square root. Sorry, I forgot a square root of vector a dotted with itself. So plugging in all those numbers, following similar steps, distributing the dot product. I got a final answer of the norm of vector a is 4.256. So if you follow all those same steps, I think we've done enough norms in this video, so I'm just going to leave this one for you to do on your own. I get the norm of vector a is 4.256 meters per second squared. So I want you to do that one for yourself, test yourself out, and make sure you can get that answer. And now we're going to combine all of this work together, and we're going to solve for theta. So I want to extract theta out of this equation. So first, I'm going to divide both sides by the norm of a and the norm of v. And so that moves them over to the left-hand side of the equation. So I get cosine of theta is v dot a divided by norm of v times the norm of a. And now to get theta, I need to do the inverse cosine of both sides. So I get inverse cosine of v dot a, all divided by the norm of v times the norm of a. And so now I just plug in all my answers that I got from the previous steps. So theta is going to be the inverse cosine. V dot a, we got an answer of negative 18.95. Let me just check that and make sure that's the exact we got negative 18.952. So I'm going to be really exact and put that in there. And that was meters squared over seconds cubed. For the norm of V, we got 4.458. And that was meters per second. For A, I let you do it, but you can check my answer. I got 4.256. That was meters per second squared. Notice that all these units cancel out. So the units in the top of the fraction cancel out with the units in the bottom of the fraction. And so my final answer is the inverse, theta is the inverse cosine of, I get negative 18.952 divided by 4.458 divided by 4.256. I get negative 0.99888. And so when you take that, you should get a final answer that theta, the inverse cosine of that answer is 177.3 degrees. So these vectors were almost anti-parallel with each other. That angle is very close to 180. So these vectors were almost completely opposite from each other, just about. All right, and that's my final answer. That's how I got the angle between those two vectors without even seeing them. I know at least what the angle between them is. All right, so that's all the work. I really do want to see all those steps. Please show me that you know what you're doing, because a lot of times students just kind of plug in randomly like zeros and 90s and 180s, and they're not really sure why they're doing what they're doing. If you write out all these steps, you will know why you're doing what you're doing. It'll really help you learn this material, so please follow that.